Hi, in this video, we're going to take a look at Chapter 1, General Overview of Fundamentals of Biostatistics by Bernard Rosner, which is a Cengage textbook. All right, so let's get into it. All right, so for our introduction, what is statistics? Statistics, according to this author, is a science whereby inferences are made about specific random phenomena on the basis of relatively limited sample material. All right, so we're taking data and converting that into insights. All right, now mathematical statistics. This is where we are developing new methods of statistical inferences and requires detailed knowledge of abstract mathematics and its implementation. So we're taking deeper mathematical understanding of other aspects of mathematics, pulling those in to use in the realm of statistics. Now, applied statistics involves application of mathematical statistics methods to specific subject areas such as economics, psychology, public health, etc. Biostatistics is a branch of applied statistics that applies statistical methods to medical and biological problems. Standard statistical methods may not necessarily be applicable for all studies. New biostatistical methods are developed by biostatisticians. All right, so what this is saying is that we're going to take the specific problem that we're interested in, and we're going to look at it very critically, and we're going to convert what we have into a math problem where we can study the data. So we're taking a deeper understanding of mathematics, pulling it in, and structuring things to get the most information out of the data that we have. And we're doing this specifically for a biostatistical problem. Really, what field is involved doesn't really matter, but biostatistics tends to use the same techniques over and over. All right, the role of biostatistics in medical research. First of all, observation. So let's say that we're looking at blood pressures, and we've got an automatic device that the patient puts their arm through, and the machine inflates the sphygmomanometer and then takes a reading. We also have the old school way where someone uses a stethoscope and listens to what's going on through the stethoscope, and we see that we get different readings. All right, well, can we draw an inference off of this? Which one is more accurate than the other? We'd like to know. So, we want to know, is there a statistical difference in blood pressure readings between the automatic machine and the human observation? Are the two methods really reading the same thing, or are they reading something different? So, study question. Are the methods of automatic versus manual determination of blood pressure comparable? Can we consider them the same? If they're not considered the same, can we mathematically convert from one to the other? To address this question, we designed and carried out the following small-scale study of blood pressure monitoring machines. All right, so the planning step. All right, something I want to impress upon you is that anytime you're doing anything with data, it doesn't matter if it's biostatistics, machine learning, experimental design, psychology, psychometrics, whatever, the earlier steps are the most important steps, because if you make a mistake early on, that mistake is going to propagate through the rest of your study. So the early steps are the most important ones. So here, the planning step is going to be the most important one that we're going to talk about. So some questions that we're going to need to answer. What number of machines do we need to test? What number of participants for each machine needs to be tested? Now, does the order of taking the measurements matter? We could do manual and then automatic, or we could do automatic then manual. Does that make a difference? Would we get a different result if we did all manual then automatic, or if we did all automatic then all manual, or we switch it up somehow? Critical data to be captured via questionnaires to aid in comparison between the methods. So it might be that there's some other variable that we don't know about at this moment, we don't know yet, that is impacting the difference in the two numbers. So what we're going to do, we're going to kind of put out a survey and collect some more data and just see is there anything that just happens to kind of blip in the data? Also, we want the format of recording data to ease future data entry into computers. All right, so what this is saying is that when we record the information, we want it to be simple for the person to enter, and we want it to be simple for the person who puts it from the entry into the computer. And also, we want to check the accuracy of computerized data. All right, so let's determine our test variables. So number of machines to be tested, we're going to do 4, since machines may or may not be comparable in quality. Now, number of participants, we're going to go with 100 people to test at each location based on sample size determination methods. We'll talk about sample size determination during the semester. And to rule out any effects that the measurement method may have, the order of measurement was randomized. So what we're going to do, we're going to flip a coin, and if it's head, we do manual first and then automatic second. If it's tails, we'll do the automated machine first, manual second, something like that. Or more than likely we would use a random number generator instead of flipping a coin, but something to just generate random numbers. All right, so some information that we're going to want to have. Anything that we know of that would impact blood pressure, we would definitely want to include in our questionnaire. So we'll include age, sex, hypertension history, body size. And and the reason why we're pulling this in is because we know that body size can influence the accuracy of the readings. So if it ends up that body size is impacting accuracy more on one method than the other, we could see the difference arising from that. Now, for the format of recording data, to ease future data entry into computers, each person assigned a unique identification number. All right, this will be important for keeping our bookkeeping straight. We're going to be using a coding form that was keyed in and verified, and we're going to use the same coding form entered twice to ensure accuracy of records. Now we're going to check the accuracy of computerized data. We're going to use editing programs to check that all variables values fell within a reasonable range of values. Outliers or aberrant values will be manually checked. So if we see something strange in our data, we're going to go and we're going to double check that. Maybe the person just kind of slipped. They meant to hit a 9 and they actually hit a 0. They meant to hit 0, they hit 9. Something like that. Anything that's weird, we'll double check. It may be they meant to put a 0 and they put an O when they were typing it in. Maybe the person who wrote it down, their handwriting is poor. Double check it. All right, so the steps. So everything we've talked about is our game plan. And we haven't actually collected any data. We have not looked at any patients, any subjects yet. All we've done is set up our plan of attack. And then we're going to execute data collection, data entry, data editing, then data analysis. Remember, any mistake I make in the process propagates through the process. So if my plan is poor, everything else is going to have a negative impact. If I make a mistake on data entry, that's going to propagate to data editing and data analysis. Now, for the data analysis phase, the data obtained from the study can be summarized using descriptive statistics, which we'll talk about. Descriptive material can be numeric or graphic. If numeric, the data can be tabulated or presented as a frequency distribution. If graphic, data can be summarized pictorially. The choice of numeric or graphic representation statistics is dependent on type of distribution of data. For continuous data, this is where there are infinitely number of possible values, such as blood pressure measurements. If we were super precise, we could have super precision in our blood pressure measurements. And so we'll treat blood pressure as a continuous variable. So we'll take means and standard deviation may be used. Discrete data, this is where there are only a few possible values, such as sex. The percentages of people for each value may be considered. Now we're going to tabulate the results of the study. And so here for this table, we have the mean blood pressure and difference between machine and human readings at 4 locations. So we have locations A, B, C, and D. we can see that we have we have less than 100 at each location. Here is the machine measurement, average, standard deviation of the blood pressures for the machine. Here is for the old school manual way, we have the average and we have the standard deviation. And something that jumps out at me right off the bat is when you look at this, you notice that the human one is always less. So, I mean, that's something kind of interesting, right? So here is the mean of the differences, and here's the standard deviation of the difference. So meaningful data for all 100 people at each test site could not be obtained on account of a few non-valid readings from the machine. Missing data is common in biostatistics and should be anticipated in the planning stage. All right, so missing values come up when, for some reason, we weren't able to record it. Maybe the subject left, maybe the machine broke down, maybe the employees left before they were supposed to, whatever. This is going to happen. This will be an issue in any realistic, true study involving data. Notice the apparent difference in blood pressure readings between machine versus manual measurements in locations C and D. So you'll notice that we have pretty big values here. So A and B are pretty close, but C and D, that's kind of big. All right, now inferential statistics. So descriptive statistics, we are describing the data we have. Inferential is where we make an inference. All right, so what we want to do, we want to determine whether the difference in blood pressure reading is just by chance, or there's some actual trend going on that going on. So a sample size of 98 people from a general population with an estimated mean difference of 14 millimeters of mercury. The error in estimated mean difference, I don't know. True mean difference, I don't know. Inferring the characteristics of a population from a sample is the central concern of statistical inference. To accomplish this aim, we need to develop a probability model which would tell us how likely it is to obtain a 14 millimeters of mercury difference between the two methods in a sample of 98 people if there were no real difference between the two machines over the entire population of users in the machine. A small enough probability would indicate that the difference between the two methods is real. Okay, so our idea here is that we're going to use probability to measure what's going on. Now, honestly, we could use other fields of mathematics, but the one that is the most complete and succinct for the purpose of data analytics is use probability. What we're going to do, we're going to say, I believe that this probability distribution is the correct one to use. I'm going to take my data, I'm going to take my probability distribution. I'm going to check to see how likely am I to see what my data is telling me. If the likelihood of seeing the result from my data is very small, then I probably have the wrong probability distribution. So if what I'm seeing is unlikely with my probability distribution, then my probability distribution is probably wrong. Make sense? And so if it's probably wrong, then I'm going to use that piece of information to reach a better conclusion. All right, so for our study, we used a probability model based on the t-distribution. All right, so the probability was found to be less than 1 in 1,000 for each of the machines at locations C and D. The low probability indicates that there is a real, or I should say a likely difference between the automatic and manual methods of blood pressure determination. So what we're doing is we're saying, you know what? I'm going to take the point of view when I choose my probability distribution. I'm going to take the point of view that machine and manual are equal. Okay, if the machine and manual are equally likely in occurring, then I'm going to use that piece of information to come up with a probability distribution. Now I'm going to compare my observed data to that probability distribution. If it works out that the likelihood of my observations, given that probability distribution, is very, 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 very low, then I conclude that that probability distribution is wrong. All right, so we came up with the conclusion that it's less than 1 in 1,000. If it's less than 1,000, less than 1 in 1,000, then you know what? I probably have the wrong probability distribution. That means I know what direction to go in to figure out what's going on. All right, so the probability distribution I picked was one assuming that machine and manual have equal likelihood distributions. All right, so I would conclude that they're not equal to each other. All right, and we're going to do further analysis using statistical packages. So statistical packages has a collection of software and statistical programs that will run the data for us. We don't have to do things manually. We don't have to use pencil and paper. We don't have to use old school calculators. We don't have to use our phone calculators or anything like that. So an example of these are SAS, SPSS, Stata, Minitab, and Excel. By far, Excel is the most common platform for statistics by far because it's so accessible. SAS is used frequently in biostatistics, and anytime you have government oversight. SPSS tends to be favored by social scientists. For me personally, I use R and Python professionally. And final step is to show the world our results. Take our results, show them to our stakeholders, and present them with our results and attempt to convince them of our conclusion. Well, that's all I've got for you. Take care and goodbye.